What if the emptiness between the stars is not empty at all? Voyager 1 has detected a faint signal where scientists expected silence, and the truth behind it may change how we see our cosmic home. Before we follow that signal into the darkness, tap like, subscribe for more journeys beyond the known, and share this video with someone who still looks at the stars and wonders what is hiding there. More than 15 billion miles from Earth, a machine built in the 1970s is still moving. It has no camera watching the road ahead. It cannot turn around. No astronaut can reach it. If something breaks, engineers cannot replace a part or tighten a loose connection. They can only send instructions across the darkness and hope the spacecraft hears them. That machine is Voyager 1. Its technology is older than the personal computer. Its memory is tiny compared with a modern phone. Its transmitters send signals so weak that by the time those signals reach Earth, they are almost lost inside the natural radio noise of space. Yet Voyager 1 is still speaking, and hidden inside its faint transmission is evidence that interstellar space is stranger, more active, and more complicated than scientists could directly prove before. Some headlines describe the discovery as impossible. That word sounds dramatic, but there's a real mystery behind it. Voyager did not discover an alien message, a secret planet, or a crack in reality. What it found is scientifically more believable, but in some ways more important. It detected a continuous, narrow signal produced by plasma beyond the sun's protective bubble. Scientists had expected to measure plasma there. What surprised them was how clearly and persistently the spacecraft could hear it. The signal continued across an enormous region, allowing researchers to trace the density of interstellar plasma almost continuously. It was like placing a microphone in a place everyone had described as quiet, then hearing a low cosmic hum that never seemed to stop. To understand why that matters, we need to return to a very different world. On September 5th, 1977, Voyager 1 lifted off from Cape Canaveral, aboard a Titan 3D rocket. The spacecraft was not originally built to explore interstellar space. Its main mission was to visit Jupiter and Saturn during a rare alignment of the outer planets. That alignment allowed engineers to use gravity as a tool. When Voyager flew close to a giant planet, the planet's motion and gravity changed the spacecraft's path and increased its speed relative to the Sun. This maneuver is called a gravity assist. It was elegant, efficient, and necessary. Voyager did not carry enough fuel to push itself across billions of miles. Instead, it borrowed momentum from planets. In March 1979, Voyager 1 reached Jupiter. Its images revealed a world far more violent and complex than distant telescopes had shown. Jupiter's atmosphere twisted into enormous storms. Its moon Io was covered with active volcanoes, making it the first place beyond Earth where active volcanic eruptions were directly observed. That discovery alone changed planetary science. Then, in November 1980, Voyager reached Saturn. It examined the planet's rings, studied its moons, and passed close to Titan. Titan's thick atmosphere was so scientifically valuable that mission planners chose a flight path designed to study it. That choice also sent Voyager 1 upward, away from the flat plane in which most planets orbit. It could no longer continue toward Uranus and Neptune. Voyager 2 would make those visits instead. Voyager 1 now had a new path. It was leaving the neighborhood. Its original planetary mission ended, but the spacecraft kept working. NASA renamed the next stage the Voyager Interstellar mission. This was not a quick extension. The distance ahead was almost impossible to imagine. Light from the sun reaches Earth in about 8 minutes. It reaches Neptune in roughly 4 hours. A radio signal traveling between Earth and Voyager 1 now takes more than 23 hours in one direction. That means every command demands patience. Engineers transmit an instruction today. Nearly a day later, Voyager receives it. If the spacecraft answers immediately, the reply still needs nearly another day to return. A basic conversation takes almost 2 days. And Voyager does not know that decades have passed on Earth. It does not know that the engineers who built it grew old. It does not know that the internet appeared, smartphones filled our pockets, or spacecraft landed on Mars. It simply follows its instructions, measures its environment, points its antenna toward a tiny distant target, and calls home. For years, Voyager traveled through a region dominated by the sun. The sun does more than shine. It constantly releases charged particles known as the solar wind. These particles flow past Earth and spread through the planetary system. As the solar wind moves outward, it creates a vast bubble called the heliosphere. Earth exists deep inside this bubble. So do the other planets. The heliosphere helps reduce the amount of galactic cosmic radiation reaching the inner solar system, although Earth also depends heavily on its atmosphere and magnetic field for protection. Far beyond the planets, the solar wind begins to slow. Eventually, it meets the matter and magnetic fields between the stars. The boundary where the outward pressure of the solar wind balances the surrounding interstellar medium is called the heliopause. Before Voyager, no functioning spacecraft had crossed it. Scientists had models, remote observations, and theoretical predictions. But a model is not the same as placing an instrument directly inside the environment. That finally happened on August 25th, 2012. Voyager 1 crossed the heliopause and entered interstellar space. There is an important detail here. People often say Voyager left the solar system, but the meaning depends on where we draw the border. Voyager escaped the heliosphere, the sun's bubble of charged particles. However, it has not escaped the sun's gravity or traveled beyond the distant Oort cloud, which may extend thousands of times farther than Earth's orbit. Crossing the heliopause was still historic. For the first time, a human-made object entered the local interstellar medium and continued sending measurements from the other side. Scientists looked for several signs. Particles associated with the solar wind dropped sharply. Galactic cosmic rays increased, the surrounding plasma became denser. Those observations showed that Voyager had crossed into a new environment. But one expected change did not happen in the simple way many researchers imagined. Scientists thought the direction of the magnetic field might rotate dramatically when Voyager passed beyond the sun's influence. Instead, the field direction remained surprisingly similar. That did not mean Voyager had failed to cross the boundary. The particle measurements were strong evidence that it had. It meant the boundary itself was more complicated. The interstellar magnetic field may bend or drape around the heliosphere. Solar and galactic magnetic structures may interact near the edge. The border is not necessarily a clean shell separating two perfectly independent regions. Nature rarely respects the simple lines we draw in diagrams. Voyager had reached the first great surprise. The boundary around our solar neighborhood was not behaving exactly as expected. Then the spacecraft began hearing something even more unusual. Voyager carries an instrument called the plasma wave subsystem. It does not record ordinary sound because space is too thin for sound waves to travel as they do through air. Instead, the instrument detects electric field changes connected with waves in plasma. Plasma is sometimes called the fourth state of matter. It is a gas in which electrons have separated from atoms, leaving electrically charged particles. Stars are made largely of plasma. Solar wind is plasma. Much of the thin material between stars is plasma too. When particles in plasma oscillate, they can produce measurable electrical signals. The frequency of those signals can reveal the density of electrons in the surrounding space. At first, Voyager measured strong plasma oscillations after powerful solar eruptions sent shock waves far beyond the planets. Imagine a storm on the sun powerful enough to disturb space more than 100 times farther away than Earth. Months later, that disturbance could reach Voyager and make the local plasma ring. These events gave scientists valuable measurements, but they were occasional. Then researchers found something much fainter. Beginning in data collected around 2017, Voyager's plasma instrument detected a narrow, persistent emission. The tone shifted slowly as the spacecraft moved through interstellar space. It was weak. It did not arrive like an explosion. It appeared as a delicate line inside years of data. That faint line allowed scientists to follow changes in plasma density even when no major solar shock was passing. The impossible part was not that plasma existed there. The surprise was that Voyager could detect a stable background signature across such a long distance, revealing detail that earlier measurements had missed. Interstellar space was giving humanity a continuous whisper. If this 48-year-old explorer has already earned your respect, leave a like as its tiny signal of support from Earth. Subscribe to join the next mystery and send this video to one curious person who would appreciate what Voyager is still doing alone in the dark. The finding was reported by researchers in the journal Nature Astronomy in 2021. The data showed that Voyager had followed the emission across billions of kilometers. As its measured frequency changed, scientists could estimate how the electron density changed along the spacecraft's path. This produced something close to a continuous map through one thin line of interstellar space. That line matters because our knowledge of the region surrounding the heliosphere is still limited. Telescopes can observe light from distant objects passing through interstellar material. Scientists can study how that material absorbs or scatters radiation. They can also build simulations based on known physics. But Voyager offers something different. It is there. Its instruments are touching the environment they measure. The difference is like studying an ocean from photographs taken on shore, then finally lowering a sensor beneath the surface. The first direct readings may confirm some predictions. Others may expose details that were invisible from a distance. Voyager revealed that the plasma around it was not perfectly smooth. Its density changed along the route. Those changes suggested structure on different scales. That does not mean space is packed like Earth's atmosphere. The interstellar medium around Voyager remains incredibly thin. A cubic centimeter may contain only a small number of particles, yet thin does not mean meaningless. Over enormous distances, even sparse plasma can influence magnetic fields, cosmic rays, and the shape of the heliosphere. It can also carry waves and disturbances. This creates a more accurate picture of the void between stars. It is not an empty black stage where nothing happens. It is a changing environment made from particles, radiation, fields, and motion. It has something that could loosely be called weather. Not weather with clouds and rain, but changes in density, pressure, magnetic structure, and energetic particles. Our heliosphere moves through that environment as the sun travels around the Milky Way. The sun is not standing still. It carries the planets through the galaxy at hundreds of thousands of miles per hour. The heliosphere moves with it, interacting with the surrounding interstellar medium. Its shape may resemble a bubble, a stretched comet-like structure, or something more complex, depending on the model and the behavior of magnetic fields. Voyager 1 and Voyager 2 crossed the heliopause in different places and at different times. Voyager 2 entered interstellar space in 2018. Their measurements were not identical. That is important because a boundary this large cannot be understood from one crossing. 2 points are better than one, but they still provide only a tiny sample of a structure that surrounds the entire planetary system. It would be like trying to understand Earth's coastline after touching it in two locations. The persistent plasma emission gives scientists another clue, but it also creates new questions. What exact physical process produces the weak signal? One possibility involves natural thermal motion in the plasma. Charged particles moving and interacting can generate tiny electrical fluctuations. Another explanation may involve weak plasma oscillations, excited by distant disturbances. Researchers continue studying the details because the signal is close to the limits of what Voyager's old instrument can detect. That uncertainty is not a weakness in science. It is science working correctly. A spacecraft measures something. Researchers test explanations. Other scientists examine the methods. New data improve or challenge the interpretation. The phrase NASA confirmed something impossible should not be understood as NASA announcing that physics has failed. What Voyager confirmed is that nature can be more subtle than our expectations. It opened a window into a region that had never been measured continuously from within, and it did this with hardware designed before many of today's scientists were born. That achievement becomes even more remarkable when we consider what nearly happened in late 2023. On November 14th, Voyager 1 stopped returning readable scientific and engineering data. The radio signal still reached Earth. Engineers could tell the spacecraft was alive, but the information inside the transmission repeated in a meaningless pattern. It was as if a distant person kept calling but could only repeat the same broken syllable. The problem appeared to involve the flight data system. This system collects information from the instruments and prepares it for transmission. Voyager's computers are nothing like modern computers. They were designed in an era when memory was extremely limited, processors were slow, and every instruction had to be efficient. The team could not simply restart everything and hope. A wrong command might make the situation worse. Every test took almost 2 days to complete because of the communication delay. Engineers searched through old documents, some written decades earlier. They studied the spacecraft's architecture and designed careful commands to reveal what was happening inside its memory. In March 2024, Voyager returned a complete readout from the flight data system. That readout provided the clue. The team concluded that a small portion of memory had failed. That damaged area contained part of the code needed to package the spacecraft's data. Engineers could not repair the physical memory. They could not upload a large modern replacement program. There was not enough free space in any single location. So they created a remarkable solution. They divided the affected code into pieces and moved those pieces into different available memory locations. Then they adjusted the software so the separated sections could still work together. This sounds simple when described in a sentence. It was not. The team had to understand how changes would affect other functions. They had to preserve commands written for hardware almost half a century old. Then they had to transmit each step across billions of miles without seeing the result for nearly 2 days. On April 20th, 2024, Voyager 1 returned usable engineering data. By June, NASA had restored science data from all 4 instruments that were still operating at that time. The spacecraft launch during the presidency of Jimmy Carter had suffered a memory failure in interstellar space and been repaired by radio. No hands touched it, no replacement part reached it. Human thought crossed the solar system and reorganized the memory of a machine beyond the heliopause. That rescue may be as extraordinary as the plasma discovery itself. Voyager is not immortal, however. Its electrical power comes from radioisotope thermoelectric generators. These devices use heat from the natural decay of plutonium-238 and convert part of that heat into electricity. At launch, the power system produced far more electricity than it does today. The output drops by roughly 4 watts each year. Voyager does not operate on only 4 watts in total, as some dramatic claims suggest. Rather, it loses about 4 watts of available power annually. That shrinking budget forces difficult decisions. Heaters have been turned off. Backup systems are limited. Scientific instruments that once transformed our understanding of Jupiter and Saturn have long been silent. In 2025, NASA shut down 2 more Voyager 1 instruments to conserve power, the cosmic ray subsystem and the low-energy charged particle instrument. They were not necessarily broken. They were sacrificed to give other systems more time. Imagine managing the last lights in a distant building while the generator slowly fails. Turning one light off allows another to stay on longer, but every switch also removes a way of seeing what is outside. The mission team hopes at least one science instrument can continue operating into the 2030s, but no one can promise the exact date of the final transmission. A heater failure, memory problem, thruster issue, or sudden loss of power could shorten the mission. Voyager also needs to keep its high-gain antenna pointed toward Earth. That requires thrusters. Over time, tiny fuel tubes have become clogged by residue. Engineers have switched between different thruster sets and changed how the spacecraft controls its orientation to reduce stress on the system. Every adjustment is another act of careful survival. The spacecraft was designed for a short planetary mission. It has now operated for nearly half a century. The fact that anything still works is astonishing. Yet this creates the deepest tension in the story. Voyager is finally in the place scientists always wanted to study, but it is reaching the end of its life. For decades, the spacecraft traveled toward the unknown. Now that it is there, its power is disappearing year by year. Its plasma wave instrument remains one of the most valuable tools aboard. As long as it continues returning data, scientists can study electron density and plasma disturbances in a region no active mission can quickly replace. When Voyager goes silent, humanity will lose its most distant scientific voice. Voyager 2 may continue, for some time as well, but it faces the same declining power and aging hardware. No new spacecraft is currently close to replacing either mission. New Horizons is traveling through the outer solar system after visiting Pluto and the Kuiper Belt. It is moving outward, but its path and speed mean it will not cross the heliopause anytime soon. Scientists have proposed an interstellar probe designed specifically to explore the heliosphere and the space beyond it. Such a mission could carry modern instruments, measure the boundary in far greater detail, and travel in a direction chosen to answer questions Voyager was never designed to investigate. But even if a new interstellar mission were approved, built, and launched, reaching the heliopause would take decades. Space is that large. Voyager's window cannot be replaced with a quick launch. And that makes every surviving measurement valuable. If you want humanity to keep asking questions that may take generations to answer, write, keep exploring in the comments, then subscribe and share this journey, because curiosity only survives when people decide the distant unknown still matters. There is another misunderstanding worth clearing away. Some descriptions turn the heliopause into a burning wall with temperatures of tens of thousands of degrees. The plasma near the boundary can indeed have a very high measured temperature, but temperature in extremely thin plasma does not feel the way temperature does in dense air. Temperature describes the average energy of particles. In deep space, those particles are separated by huge distances compared with particles in Earth's atmosphere. There are too few of them to transfer heat quickly to a spacecraft. Voyager did not fly through a solid curtain of flame. It crossed an invisible region shaped by magnetic fields, charged particles, pressure, and energy. That truth is less cinematic, but far more interesting. The border of our solar neighborhood is not a wall, it is an interaction. Particles from the sun meet matter from the galaxy. Magnetic fields bend and respond. Solar eruptions travel outward and continue affecting plasma. Far beyond the planets, the inside and outside are not completely disconnected. Our home is part of the wider galaxy. This is where Voyager's discovery becomes personal. The heliosphere influences how many high-energy galactic particles enter the planetary region. Those particles come from events such as exploding stars and other energetic processes. Earth is not defenseless without the heliosphere. Our magnetic field and atmosphere provide powerful protection. Still, understanding the heliosphere helps scientists study radiation around planets, conditions faced by astronauts, and how stellar environments may affect the habitability of worlds. Other stars produce stellar winds and bubbles of their own. If we want to know whether distant planets could support life, we must understand how stars interact with the space around them. A planet may orbit at the right distance for liquid water, yet still face intense radiation. Its star's wind, magnetic behavior, and surrounding interstellar environment may influence whether its atmosphere survives. Voyager is therefore not only teaching us about a boundary far away, it is helping us ask better questions about life throughout the galaxy. The data also shows the danger of assuming that empty-looking regions are simple. For centuries, people imagined the space between planets as a perfect vacuum. Then science revealed solar wind, magnetic fields, dust, energetic particles, and radiation. The space between stars looked even emptier. Now, Voyager has shown us measurable changes in plasma density and a weak background emission stretching across its path. Every time humanity enters a place directly, the place becomes more detailed. The moon was once a smooth light in the sky. Telescopes revealed craters. Spacecraft revealed chemistry, ice, seismic activity, and a violent history. Mars was once a red point. Orbiters and rovers revealed dried river channels, layered rocks, buried ice, dust storms, and ancient environments that may once have supported life. Interstellar space was a dark gap. Voyager gave that gap texture. It also gave it a sound, although the famous audio versions are translations of plasma data into frequencies human ears can hear. The spacecraft itself is not hearing music in the ordinary sense. Scientists convert the electrical measurements so patterns can be studied and shared. Those eerie tones are not alien speech. They are matter responding to forces in an environment no person has visited. That may be more profound than a fictional message. The universe does not need to speak our language to tell us something. Sometimes it vibrates, and we build instruments sensitive enough to notice. Voyager's signal is extremely weak when it reaches Earth. NASA's Deep Space Network uses giant antennas in California, Spain, and Australia to communicate with distant missions. As Earth rotates, different stations can listen. The network must separate Voyager's transmission from background noise, track its exact location, and decode information sent by technology from another era. The spacecraft transmits with power comparable to a small household light bulb. By the time that energy spreads across billions of miles, the received signal is unimaginably faint. Yet information survives. A pattern created beyond the heliopause moves at light speed for almost a day. It reaches an antenna on Earth. Computers recover the data. Scientists transform it into measurements of a place humans cannot see. Think about the chain of events required for that moment. Plasma particles move in interstellar space. An instrument built in the 1970s detects an electrical fluctuation. An aging computer processes the measurement. A transmitter sends it toward where Earth is expected to be. The signal crosses a distance so large that our planet moves millions of miles before it arrives. A radio dish catches part of it. Then a human being looks at the result and learns something new about the galaxy. That is not magic. It is engineering, mathematics, patience, and trust between generations. Many of the people analyzing Voyager data today were not alive at launch. Some original team members never lived to see the heliopause crossing. The mission belongs to more than one generation because its destination required more time than a single career. That may be Voyager's most important lesson. Some discoveries demand that people begin work they will not personally finish. They must build carefully, document everything, and trust future strangers to continue. Voyager's makers could not predict every problem it would face, but they built a spacecraft flexible enough that later engineers could save it. The repair in 2024 depended not only on technical brilliance in the present. It depended on choices made decades ago. It depended on records being preserved. It depended on people refusing to abandon a machine simply because the easy solutions were gone. The mission is also carrying a message for a future that may never receive it. Attached to Voyager 1 is the Golden Record, a gold-plated copper disc containing sounds and images selected to represent Earth. It includes greetings in 55 languages, music from different cultures, natural sounds, scientific information, and images of human life. There are sounds of wind, rain, animals, footsteps, laughter, and a human heartbeat. The record was designed as a greeting to any intelligent finder, but the chance of someone discovering it is extremely small. Space is too vast, and Voyager will not pass closely by another star for tens of thousands of years. Still, the record matters. It says something about the people who launched it. They knew the darkness was enormous. They knew the spacecraft might never be found. They sent a greeting anyway. After Voyager's power disappears, the golden record will remain. The spacecraft will continue moving because interstellar space offers almost no resistance. It will pass through the galaxy long after its transmitter is dead. Barring an unlikely collision or capture, it may survive for billions of years. Continents will move. Mountains will rise and vanish. The sun will grow brighter and eventually transform. Human languages may disappear. Voyager will keep carrying its small archive. But while the record speaks to an unknown future, the scientific signal speaks to us now. And we do not have forever to listen. Sometime in the coming years, a deep space network antenna may receive Voyager 1's final transmission. We may not know immediately that it is the last. Engineers may wait for another signal. They may send commands. They may search through noise and test every possible explanation. Days could become weeks. Eventually, the team may have to accept that the conversation has ended. Voyager will not know that Earth can no longer hear it. It will continue along the same path, carrying silent instruments through a sea of plasma. The loss will not be dramatic from the spacecraft's point of view. No explosion will light the darkness. No final image will show the stars fading. There will simply be no next message. That future silence is why the discovery matters today. Voyager found that interstellar space has a persistent signal that can reveal changes in plasma density. It showed that the heliopause is more complex than a simple border. It measured particles and magnetic fields from a place that existed only inside models before 2012. None of this breaks physics. It does something better. It expands physics with direct evidence. The word impossible often appears when reality refuses to match a simple expectation. But science does not treat surprise as defeat. Surprise is an invitation. It tells us where our maps are incomplete. Voyager's map is only a thin trail through an enormous wilderness. One spacecraft moving in one direction cannot explain the entire heliosphere or the local interstellar medium, but every map starts with a line. Voyager drew the first one. Soon, in late 2026, Voyager 1 will be roughly 1 light day from Earth. At that distance, even light will need about 24 hours to travel one way. A command sent from Earth will cross darkness for a full day before reaching the spacecraft. Its response will need another day to return. That milestone gives us a new way to understand the distance. Voyager is not merely far away in miles, it is far away in time. When we hear it, we hear the spacecraft as it was almost a day earlier. And every year, that delay grows. Yet distance has not broken the connection. A machine with aging computers, declining power, and failing components is still extending the reach of human senses. Our bodies remain on Earth, but our instruments do not. Voyager is a piece of human curiosity moving between the stars. It found no monster in the dark. It found no alien beacon. It found something quieter and more honest, a universe filled with structure where we once imagined emptiness. That discovery should humble us. We have explored only a tiny part of our own cosmic neighborhood. We live inside a protective region whose true shape and behavior we are still trying to understand. Beyond it lies not a dead void, but an active galaxy. Voyager entered that environment with instruments never designed for everything they would encounter. It listened, survived, failed, recovered, and kept moving. One day, its voice will disappear, but the distance it crossed will remain part of human history. So when you look into the night sky, remember that somewhere beyond the planets, beyond the solar wind, and beyond the edge of the sun's great bubble, Voyager 1 is still traveling. Its antenna is still turned toward a world that has become almost invisible behind it. Its remaining instruments are still measuring the darkness. And buried inside an almost undetectable radio signal is a simple message from the edge of the known. The universe was never empty. We had simply never gone far enough to hear it.